at x is equal to 0 multiplied by the area is 0. The area cannot be 0, it's a physical quantity. Property of a body, thermal conductivity cannot be 0 because it is a property of the body. The material cannot get rid of it. So the only term that becomes 0 and so what I'm getting is an important thing, which is why I want to talk about it. This is called as an adiabatic boundary condition. It's a boundary condition. This is not throughout the body. This is at the boundary, x is equal to 0. The variation of the temperature as a function of x is 0, which tells me that the temperature is not 0 at that surface. That cannot be the case. This tells me that the rate of variation of the temperature with respect to a spatial quantity is 0 at that particular surface. So this is called as a adiabatic boundary condition. And in mathematics, in partial differential equations, which is all heat transfer is about, this is called as a Neumann boundary condition. You will have two types, Dirichlet and Neumann boundary conditions. The Dirichlet boundary conditions are boundary conditions for the temperature at that particular surface. If I take the first derivative with respect to space, I enter what is called as a Neumann boundary condition. And we'll talk more about this on Monday. Okay? So that's one. Then I'm going to draw the fourth one. And then eventually I'll take a look at number 2 figure and then number 4. We are done with 3 and 1. Okay? For the fourth one, surface energy balance once again at the top surface. Surface energy balance. Which implies that even if there is volumetric heat generation within the body, within the control volume, in this situation, E dot G is 0, E dot stored is 0. All the volumetric terms will vanish. At the top surface, I have everything that we had drawn for situation number 1. I'm going to have ET, then I'm going to have alpha sun, G sun, which is the irradiation coming from the sun, solar irradiation. I'm going to have likewise alpha naught, G naught. Based upon the answer that we have obtained, it is quite obvious that the heat transfer due to conduction is from the top surface to the fluid, because the fluid is at 293 Kelvin. We obtained this as 376. Even if you had flipped it around the first way, it would not change your answer, which is when you will change your directionality. Okay? So this is 2 double prime convection. This is all on the top of the control surface. At the bottom, I'm going to have conductive heat flux, which is flowing and hitting the bottom of the top surface. Yes, question?
Can you repeat why you flipped the alpha naught G naught? Sorry, I missed it. Like how flip the arrow of it? Or not the alpha naught.
This one? No, I did not flip anything.
Okay, alright, sorry about that.
Yeah. So, these are all absorbed quantities. They will always be coming towards the control surface as you're drawing them. This is an emitted quantity. This is always going out of the control surface. I don't mess with these arrows at all. Absolutely not. No matter what the temperatures are, you cannot do anything about these arrows. The only arrow that you have some sense of control over is this guy. And that too at the beginning of the problem, because I did not know what the temperature of the top surface was. But now I do know it, and so I have no control over that either. So basically somebody else is controlling my life. Alright. Which is true once you get married. Alright, that's I'm on camera. Alright, so on this surface I'm going to have conductive heat flux at the location x is equal to delta L. At x is equal to delta L. I hope my writing is clear to everybody. So this is the fourth situation. Alright, and then I write my E dot in and E dot out, and I'll be more than happy to stay after class, keep our distance, and then answer any questions you have. Okay? And bring, that reminds me. I'm going to change my morning office hour times to afternoon. I'm going to make it from 1 to 2 p.m. instead of 10 to 11 a.m. because I'm assuming some of you have class during the time. So I'll make it from 1 to 2 p.m. and then from 4 to 6. It's a marathon on Fridays. Alright, so I write E dot in and E dot out here. All the terms coming in, so this is alpha naught, G naught, alpha sun, G sun, Q double prime, as x is equal to delta L, all of this multiplied by the area of the top surface. E dot out, like before, is Q double prime convection, E suffix T, multiplied by the area. E dot G is 0, E dot stored is 0, so you write your energy balance. E dot N becomes equal to E dot out. So for any surface energy balance, you don't need to keep repeating this idea every time. If you have a surface energy balance, E dot in is equal to E dot out. No questions asked, no points taken. Okay? Unless the answer is wrong. So I'm just going to write E dot in plus alpha sun, G sun, Q double prime, conductive flux at delta L. This is Q convection and ET. We have a couple of options. We just did a lot of hard work, found out the temperature of the top surface, right? So which means that if I need to find the conductive heat flux at the top surface at x is equal to delta L at the boundary of the top surface, then I can use this particular equation here because I have all the answers known to me. So I can substitute and I can solve. Let me also revisit figure number 2 and write the energy balance from there. So from 2, please notice 2 is at the right corner of the board. If I'm standing facing the board, top right corner, I write the total energy balance. E dot N is Q double prime conduction and x is equal to 0, which we just decided is equal to 0 based upon energy balance from 3. So this is 0 based upon 3, okay, which is what we obtained from here. Then E dot out is Q double prime conduction and x is equal to delta L, and this is the same conundrum as you would see in mechanics. Which free body diagram should I use to solve for the forces? This one or that one? Could use any of them if you have enough information about all of them. Then I write E dot G. Be careful, this is not 0 because now I'm looking at a volumetric phenomenon based upon the way I've drawn the control surface in there. This is plus Q dot times V or Q dot times area times delta L, and I have to apologize, I have to write the areas here, sorry. Area times all of that. Flux times the area is the total heat transfer, right? dot stored is 0. And this was from Alright, now I write my energy balance equation. Yes, question.
So logically, if we're working against an insulated surface like we did for 3, we can assume that Q double prime conduction is 0.
Absolutely. That implicitly becomes a boundary condition every time we solve a conduction problem. And that's the adiabatic boundary condition. And we can also prescribe a Dirichlet condition, which is, if you know the temperature at the bottom surface, you can say that T at the bottom surface is some value. And that's going to remain the same no matter what, because there's no heat transfer taking place at the bottom surface. Okay, fantastic. So E dot in minus E dot out bear with me, last couple of minutes. E dot stored is history. E dot in is gone. E dot out is A times that quantity. So minus A Q double prime conduction at x is equal to delta L plus E dot generated, which is this new term that you're seeing today, Q dot, little q dot. You're going to see that fellow for a very long time from now on. And so it should be obvious from these equations that if there is E dot G, take any questions? Questions? No, no questions.
Sorry.
No, no problem. So it should be obvious that if you have energy generation within a control volume, or if you are looking at an unsteady situation, unsteady heat conduction is something we'll be looking at as well, which means that the rate of change of the stored energy is no longer 0. That's a very tricky problem indeed. If either of these two or both of them are true, then the conductive heat flux throughout the body is not the same at all points. The flux at the bottom is no longer equal to the flux at the top surface. It's quite obvious to see that's not the case. This is a non-zero value. Right? So I cancel off this A, and so Q double prime at x is equal to delta L is just Q dot times delta L. Q dot is 100 kilowatts per meter cube, so this is 100 10 to the power 3, so many watts per meter cube. Delta L was 4 millimeters, convert everything into meters. So 4 times 10 to the power minus 3 meters, or this quantity is just 400 watts per meter cube. Meter square, I'm sorry, it's a flux. And this is not equal to Q double prime conduction at x is equal to 0. And so this example was, after you write down your thoughts, this example was purposely designed to include generation to prove the point that when I start my lecture on Monday, I cannot assume at this very simplistic formula for conductive heat transfer. K by delta L times T high minus T low, that guy is history. You can forget it after the first homework.